A planet orbiting closely around two stars has surprised scientists, but it's still unclear how it came to be. While our Sun prefers to remain solitary, many other stars exist in binary systems, meaning two stars that are gravitationally bound to each other. In some cases, these stars are so far apart that planets can form around each individually. However, there are many compact binary systems where two stars orbit each other at very close distances, so close that both could comfortably fit within our solar system. In such systems, exoplanets are usually found at greater distances, orbiting both stars jointly. According to reports from Technica, scientists in a new study have described a system that does not fit into any of the above categories. This system is a compact binary, featuring a heavy central star around which a white dwarf revolves at a distance of about 2 to 3 times the distance from the Earth to the Sun, 2 to 3 astronomical units. The presence of a planet has been definitively confirmed within this system, squeezed between the two stars and orbiting at a distance similar to that of Earth from the Sun. Interestingly, this planet is orbiting in the opposite direction to the motion of the white dwarf. The discussed exoplanetary system, named Nova Octanis, has a main star with a mass approximately 1.6 times that of our Sun. Its companion star is significantly dimmer, with about half the mass of the Sun, orbiting the main star. The orbit of this companion star around the larger star is somewhat asymmetrical, varying from about 2 astronomical units at its closest to about 3 astronomical units at its furthest point. However, until recently, the precise nature of this star was unknown. Precise imaging of the system in near-infrared light should have made it possible to distinguish the two stars from one another, but it couldn't detect the second body with enough brightness. This ruled out the presence of any type of main sequence star, leaving only the white dwarf as the likely remaining option. However, this star was not the only object in the orbit around the central Nova Octanis star. Previous research hinted at the potential existence of an exoplanet in the system. Yet the orbital characteristics of this planet were very strange, as no stable model for its orbit compatible with observations could be found. The only clear point was that the most stable orbital models could only occur if the planet moved in a retrograde direction, meaning against the spin of the companion star. Therefore, Nova Octanis became one of the mysteries that required more data for resolution. And the additional data was precisely what a small international team of scientists gathered over nearly 2 years of observations using the HARPS, High Accuracy Radial Velocity Planet Searcher, instrument in Chile. The obtained data clearly confirmed the existence of a planet in a retrograde orbit and also demonstrated that the orbital plane of this planet deviates by about 17 degrees from the orbital plane of the two stars. Unfortunately, numerical modeling showed that over time, 98% of these orbits become unstable in less than 50 million years. Thus, the researchers examined a set of orbital characteristics that could keep all bodies within a shared orbital plane. This investigation resulted in a model that, after applying various modifications, showed that in 75% of cases, the orbits remain stable for more than 50 million years. Therefore, the researchers selected this model as the most likely description of the structure of the system. In this final model, the orbit of the identified planet in the Nova Octanis system is retrograde, meaning it moves in the opposite direction to the motion of the smaller star in the same system. This planet is located at a distance of about 1 astronomical unit from the central star, roughly equal to the distance from Earth to the Sun. Its orbit is not perfectly circular but somewhat oval, getting much closer to the central star at points along its path. The important point here is that the entire orbit of the planet is situated within the orbit of the smaller companion star. The gravitational forces within a close, compact, binary system should naturally prevent planetary formation in this region during the early stages of the system's life. So, the question is, how has this planet come to exist in such an unusual configuration? The fact that one of the stars in the Nova Octanis system is a white dwarf raises some possible explanations. White dwarfs originate from stars similar to the Sun that have undergone an advanced phase of helium burning. During this phase, the star significantly expands, causing its outer layer to have a weak bond with the remaining mass of the star. Within the environment surrounding the nova outburst, these conditions can cause a significant amount of material from the outer companion star to be stripped away and drawn to the surface of the current central star. The final result of this process is a substantial transfer of mass. There are two scenarios for a planet to be located in the inner part of the system. Firstly, the transferred material is unlikely to land immediately on the surface of the nearby star. If this process has proceeded slowly enough, it could create a transient protoplanetary disk, allowing enough time for a planet to form in the inner region of the system. Alternatively, if planets were orbiting at locations outside both stars, a change in the mass distribution of the system could destabilize their orbits. This instability might lead to interactions among the planets, sending one of them into the inner system and ultimately trapping it in a stable, retrograde orbit that we now observe. The authors of the study emphasize that each of these scenarios should be quite rare, meaning that we are unlikely to observe many systems similar to this one at the current stage of exoplanet surveys. They mention another compact binary system called HD 59686, which appears to have a planet in a retrograde orbit. However, like Nova Octanis, the data is not sufficiently clear to definitively rule out alternative configurations. Therefore, it must be reiterated that more data is needed.